So in 4.3b, we're going to be given two graphs in example 1. The first graph is f prime of x. And it looks like this. So that's f prime. And the second graph is f double prime. And it looks like this. So I'm given two graphs, f prime of x and f double prime of x. And our job is to sketch the original f of x. So they gave us a graph of f prime. They also gave us a graph of f double prime. And what we are trying to do is sketch the original f of x. I'll put that over here. So I'm going to start out looking at the graph, both graphs from 0 to 1. So from 0 to 1, f prime has negative values because it's below the x-axis. So if f prime is negative, what does that tell us about the original graph? Decreasing, right? If the slope is negative, then the original graph is going down. So right here, that tells us that it's decreasing, it being f. Okay, now I'm going to look at f double prime from 0 to 1. And during that interval, 0, 1, f double prime is negative. So what does that tell us about f? Concave down, right? If f double prime is negative, then the original graph is concave down. So if we're going to draw a graph of f from 0 to 1, it needs to be decreasing and concave down. So we'll just go over here and do that from 0 to 1. And it's a little bit awkward because I don't know where to start, but that's okay because f prime and f double prime, if that's the only information we have, that just tells us about the shape of the graph. It doesn't tell us where the graph is. So all we have to do is sketch a graph that is the right shape. So we can start anywhere. So I'll just start here, I guess. And I need it to be decreasing, concave down. So that looks like this. That's a graph that's going down and is concave down. So now I'm going to move on to the interval 1, 2. From 1 to 2, f prime is still negative.
Pardon the interruption. Those students for the alphabet that starts with A through E, if you need to have your pictures retaken or if you haven't had it before for your student ID, please go to the wrestling room at this time. Thank you.
And also, all seniors still want their picture taken right, so you're in the composite, even if you're doing, did everybody do that too? Like you want it taken down there either for, okay. Sometime today. All right, so here f prime is negative, so that means the graph is still decreasing because f prime is still below the x-axis. But over here, f double prime is positive because it's above the x-axis. So that means it's concave up, it being f. So from 1 to 2, f prime is negative, so f is decreasing, and f double prime is positive, so f is concave up. So now we're going to go over here, and from 1 to 2, draw a graph that's decreasing concave up. So that's like this. All right, now let's look at 2 to 3. From 2 to 3, f prime is above the x-axis, so f prime is positive. So that means that f is increasing. And then right here, f double prime is still positive because this graph is above the x-axis, so it's concave up. I'm saying it, and that's bad. You should always say f, f prime, etc. I mean f is concave up. So now I got to draw a graph that's increasing concave up. So that looks like this. That part is increasing and concave up. And then finally, from 3 to 4, this graph, meaning f prime, is positive, so f is increasing. And then from 3 to 4 here, f double prime is negative, because this graph is below the x-axis. That means the f graph is concave down. Downward concavity. So I'm going to draw over there a graph that's increasing, that's concave down. So that looks like that. That little piece there is increasing and at the same time concave down. Okay, so that's what I remember. It doesn't matter where you start, because this graph, the f prime graph and the f double prime graph, they just tell you the shape. So all you can figure out is what the shape of the graph is. You can't figure out where it starts. So that's why I just started randomly up there. But there's no reason why I should have started up there. I could have had the same exact shape, but just down there instead. Is everybody doing okay with that? Okay, so that's example 1. Example 2 has a bunch of information in it, which I do need to write down for the camera, but you don't need to write down because I copied it for you. So while I'm writing it down, look at the information and think about what it says. So lots of stuff there, so try to digest it while I'm writing it down here. So first of all, it says f is continuous at the top there on the interval -3, 3. And then it also says that f is an odd function. So that's some information that we'll have to figure out what exactly that means. Then there's some values that are given. So when x is 0, 1, 2, and 3, f is 0, 2, 0, and -2. And then f prime is 3, 0, doesn't exist, and -3. And then f double prime is 0, -1, does not exist, and 0. So there's some values given. So this row in particular is going to tell us where to draw the graph. So on the last one, we didn't really know where to start. But this is telling us that we have the point 0, 0, and that we have the point 1, 2. So that'll help us figure out exactly where the f graph should be, unlike the last one where we just had the shape of the graph. Okay, then there's information about the derivative and the second derivative. So the f is positive, positive, negative on those intervals. F prime is positive, negative, negative on those intervals. And f double prime is negative, negative, negative. And of course what we're going to do here is sketch a graph of f. Okay, so I did that quickly. Did I get all that stuff written down right? All right, so that's a lot of information. We're going to take all that information and draw a graph for f. Okay, so first of all, we've got some points, right? 0, 0 is a point on f of x, according to this. And then 1, 2 is another point. And then 2, 0. And 3, -2. I'm getting myself into trouble here. I need to leave some more space. So 0, 0, 1, 2, 2, 0, and 3, -2. So that's a little bit easier than last time. I've got some points to go off of, some anchors. All right, now I'm going to turn to this information here. What does it mean if f is positive from 0 to 1? It means it's above the x-axis. Okay, what does it mean if f prime is positive from 0 to 1? The graph of f is increasing. The slope is positive, so the graph's going up. And then what does it mean if f double prime? F double prime is negative from 0 to 1. Concave down. So I got to draw a graph that's above the x-axis, that's going up, and it's concave down. So I'll just connect these, going up, concave down, above the x-axis. There it is, going up, concave down above the x-axis. All right. So now let's see here. From 1 to 2, it's still above the x-axis, right? But then it's going down, still concave down. There you go. That's fine. All right, so still above the x-axis, going down, concave down. So that looks like that. Okay, and then the last bit says below the x-axis, going down, concave down. Below the x-axis, going down, concave down. So that's kind of weird looking, but that's what it told me to do, right? Okay, now let's look at these values here. Apparently, the derivative is 3 at 0. So let's see if that's feasible here. I think it's I've got my graph a little too steep, don't I? I don't believe that that's 3. So I'm just going to make it a little less steep there. Still concave down, still going up. I just, at 0, I needed it to be a little less steep because my derivative was supposed to be 3. There. Okay, now what's the derivative supposed to be at 1? 0. So as long as that's smooth in there, maybe I could clean it up a little bit, but I want it to be a 0 slope there. At 1. So now that's good. That looks like a 0 slope at 1. Okay, what's happening to the slope at 2? Doesn't exist. Is that happening here? Yeah, because I've got a corner point. Since I have a corner point at 2, that means the slope doesn't exist. And then at 3, it's supposed to be -3. And I can believe that this slope is pretty close to -3. And then that bottom row of f double prime, that's really not important information. The only reason I put it down there is because the problem in your book also includes that information. I didn't want you to be thrown off by that. Don't pay attention to the f double prime values is what I'm saying. Okay, there's one piece of, so let's double check up here. Is my graph continuous? So far, yeah, but it's not continuous from -3 to 3, it's just continuous from 0 to 3. So I'm going to have to extend the graph somehow. And this is how I'm going to do it. The f is odd tells me something. So an odd graph it's a graph that if you rotate it 180 degrees, it's still going to match up with itself. That's what odd is. So I need to take this and rotate it 180. And so it'll end up looking like this. And I always have trouble rotating this last piece. That part I can rotate. This piece is a little tricky. I think it would end up looking like this. See that rotating up to there? So I got all of this over here by the fact that f is odd. And again, odd means rotate it 180 and then it matches up with itself. Okay, so that's just taking all the stuff we've been doing, all the information that we've been getting, and sketching a graph from that information. So we know where it's increasing and decreasing based on the first derivative, and we know where the concavity is based on the second derivative. All right, so just to summarize what's been happening, we had the closed interval method for finding absolute extrema. We had the first derivative test for finding local extrema. And then at the same time, you figure out where f is increasing and decreasing. And then we had the concavity test yesterday, which is figuring out where the graph is concave up and concave down. And on the side, you also figure out the inflection points based on that test. Okay, so now we're going to have one last test. This is called the second derivative test. And the second derivative test is an alternate method for finding local extrema. So we had the first derivative test, which is a method for finding local maxes and mins. And now we're just going to have the second derivative test, which is another way to find local extrema. But this way has a downfall. It only works for the critical values. So remember, local extrema might happen at critical values. So this one only works for the critical values that come from the derivative being 0. So there are two types of critical values, right? There are some critical values that come from f prime being 0, and then there are others that come from f prime being undefined. All of those values are called critical values. And all of those could be places where there are local extrema or even absolute extrema. So critical values are important for all those reasons. But there's two types of critical values. And this method, this alternate method, only applies to the ones that come from f prime equal to 0. So you're not going to be able to use this method if f prime is undefined somewhere. It won't work for that. Okay, but anyway, it's the second method, and here's how it works. It says if f prime equals 0 at c, so if f prime of c is 0, and f double prime at c is negative, then f has a local max at x equals c. If f prime is 0 and f double prime is less than 0, then f has a local max. So let's digest what this says, and then we're going to see why it's true. So first of all, if f prime is 0, that means that the slope is 0. And then if f double prime is less than 0, that means that the graph is concave down. So picture a graph that has a 0 slope and is also concave down. Doesn't that look like this? So that's why it's a local max. On the other hand, if the slope was 0 and it was concave up, then it would be a local min, right? So that's the second part of the second derivative test. If f prime is 0 and f double prime is positive, then f has a local min at x equals c. All right, so this would be example 3, and we've got y equals x cubed plus 3x squared minus 2. And we're going to find the local extreme. Okay, so according to, well, I could do this problem using the first derivative test. Because anytime you're trying to find local maxes or mins, that's a method. But since we just learned this other method, I'm going to use this one. But it doesn't matter which one you do if you have this type of a question. All right, so since I'm going to use the second derivative test, that means I need both the first derivative and the second derivative. So I'll take both of those derivatives. And the first derivative is 3x squared plus 6x. And then the second derivative is 6x plus 6. So it's nice to have non-complicated derivatives. Those are pretty easy. Okay, so then I need to find the critical values. I need to find where the slope is 0 and also where the slope is undefined. Because that's where the locals might happen, right? So I'm going to set 3x squared plus 6x equal to 0, and 3x squared plus 6x equal to undefined. This never happens, right? Because when you have a polynomial, it's never undefined. Why am I happy about that on this problem? Because that means I could use my new test that I just told you about. If there had been some undefined critical values, then the first derivative test would have been the only thing we could use. Okay, so I got to solve this equal to 0. So I'm going to factor out the 3x. So that happens when x is 0 and also when x is negative 2. So I've got two critical values, x equals 0 and x equals negative 2. So that's a possible place where there might be a local min or a local max. So then to figure out which it is, I just plug it into the second derivative. Because the second derivative test says if f prime is 0, and also if the second derivative is negative or positive, then we know some stuff. Okay, so we're going to plug 0 into the second derivative. So that's 6 times 0 plus 6, which is positive. So at 0, the first derivative is 0, and the second derivative is positive. So that means that it's concave up. So that's going to make a local min. So there is a local min at x equals 0. And then the value is, you get the value just by plugging into the original, right? So the value is negative 2. Just plug 0 in there. Okay, so then I have this other critical value, negative 2. So I'm going to plug negative 2 into the second derivative. So that is 6 times negative 2 plus 6. So that's negative 12 plus 6, which is negative 6. So now we have a graph where the slope is 0, and it's also concave down. So that's going to look like this. So that means there's a local max there. There is a local max at x equals negative 2, and the value is, let's see here, negative 2 cubed is negative 8, then negative 2 squared is 4, so we've got negative 8 plus 12, so that's 4 minus 2 is 2, so the value is 2. So I just plugged the negative 2 back into the original to figure out what the value is.
For the interruption, students with the letter F through H, if you need to have retakes or have your picture taken for your ID card, please go to the wrestling room at this time. Thank you.
Everybody good? Yeah.
On that, if f prime isn't 0, then how are you getting the negative 2?
F prime is 0 at negative 2. Yeah. And that, yeah. So there were 2 critical values. Good. All right. Anybody else? Thanks for asking. Anybody else? Okay. That's everything for A, B, but we have a shortened bell tomorrow, so I got to start BC today. So we're going to go on to that in just a second.